So anytime we're thinking about a continuous function, we're looking for three things. We're looking for no holes, no jumps, no asymptotes. Okay? So if we can draw a graph that doesn't have these things, then we know that it's going to be continuous. And so usually what we're looking for is graphs where we can draw them without picking up our pen or pencil. Okay? Most all of our polynomial graphs, we can see we can do something like that. Exponents, logarithms, linear equations, and there are others. So things like this where we can draw them without kind of picking up the pencil to form a hole, a jump, or an asymptote. Okay, so that's what we mean by continuous. So here, let's look at our formal definition for continuity. A function f is continuous at a point A if the following conditions are true. And it does mean all three conditions have to be true. First is that f of A is defined. All we mean by this is that A is an element of the domain of f. Okay? So whatever point we're looking at, in order for it to be continuous, it does have to be within the domain. Okay? For the second condition, the limit as x goes to a of f of x must exist. And if you recall from when we started talking about limits, what this means is, if I look at the limit from the left of the function, it must be equivalent to the limit from the right of the function. And more importantly, these values that we get must be a subset of the real numbers. Okay? So in this case, it is not okay to have it be positive or negative infinity, even though those limits exist and they will give us the same value. Here it does actually have to be a real number in order for it to be continuous. And then the last condition says that if I look at the limit as x goes to a of f of x, it does in fact equal f of a. And this is important because this second condition does not always imply the third. And so here we're making sure that even though the two one-sided limits agree, they also agree to whatever the function value is. So basically our limit has to equal the function value. Okay. If we have an a that does not meet one of these conditions, and again it only has to fail at one in order for it to be not continuous, then we say the function is discontinuous. If f of x is not continuous at a, then f is said to be discontinuous at a. And we can say that a is a discontinuity of f. Okay? So some of the times you're going to be asked to determine the continuity, sometimes you're going to be asked to find points of discontinuity, and other times you're just going to be asked to find the intervals for which the function is either continuous or discontinuous. When we start looking at discontinuities, there are two types of discontinuities that we can have within a function. We have what we call removable discontinuities, and these are basically where the function is continuous except at a single point, which if we redefine that point, then it would be continuous. Okay? So f is continuous everywhere except a, but if f of a is redefined, becomes continuous. F becomes continuous. And these are all functions of a particular type. Basically, these are the ones where you have holes. So for example, I might have something like this where maybe it's a continuous function elsewhere, but there's a hole and the function just isn't defined there. Or maybe I have something like this where there's a hole, and at that particular point, the function is defined elsewhere. So in both of these cases, we would consider these removable discontinuities, because if I redefined my function at the point A, then it would be continuous. So for example, in this case, if I called this value B, if I said f of A is equal to B, and my f of x is the remaining function, this would become continuous, so A would be a removable discontinuity. And then same thing here. If we redefined f of A to be, instead of this point, where we have the hole, again, it would be continuous everywhere, so A is a removable discontinuity. The other type of discontinuity we have are the non-removable discontinuities. And these are the ones in which if we look at the function, it's continuous everywhere except at that point. But if we tried to redefine the point, it still wouldn't be continuous. Okay? And the reason these would be non-removable, so examples of these, there's a couple different types. Maybe I have a function where there's a jump. Okay? So in this case, it's continuous up to this point for the left. And on the right, it's continuous up to this point. But here, there's no way I can redefine my point A so that a single value will make it continuous. There's just no way, because it jumps from one curve to the other at A. So this would be considered a non-removable discontinuity at A. Okay. We also have the ones where we are looking at asymptotes. So asymptotes can be non-removable discontinuities as well, and it's a lot for the same reason. So for example, let's say there's my A, and my function does something like this. Okay? Both are going to infinite limits, so again, there's no single point I can put here so that the whole function would be continuous. So again, in this case, A would be a non-removable discontinuity. Okay? So one of the things you're going to be asked to do is, given a function, determine if there are any discontinuities, and be able to tell what type they are. So in this example, we are given f of x equals x cubed plus 8 over x plus 2. And we want to determine first if f is continuous, and then second, we want to determine the types of discontinuities, if there are any. So here, if we look at our function, x cubed over plus 8 over x plus 2, the first thing we notice is there is a denominator in this function, and so we have to consider where the denominator is equal to 0. So here we can see that at x equal negative 2, the function is not defined. So at x equals 2, f is discontinuous. Okay. Everywhere else, if we plug in, both the numerator and denominator are going to be defined. If we look at the numerator, it's a polynomial, so any value we plug in there, we know it's going to be continuous. It's going to be defined, and the limit is going to equal the function value, which means that the limit exists. If we look at the denominator, the same thing is true. It's a polynomial, in this case a linear function. So everywhere but at -2, that function is going to be continuous. Okay? So here's our only point of discontinuity. So f is continuous on the intervals from -infinity to -2, union -2 to infinity. To determine the type of discontinuity, we actually have to look in a little more detail at the function. So here, x cubed plus 8 over x plus 2, we want to simplify this down and see if we can remove the discontinuity or if it's something that's non-removable. If it's removable, remember we should be able to redefine the function at that particular point. So here we're going to try and start by simplifying, and in this case we can see it's the sum of cubes So we can simplify by factoring out that numerator, and then we can cancel to get the x squared minus 4x plus 4. Okay, so this tells us that our function that we're starting with is basically the same as this function here. So if I redefine -2 for whatever the value is here, then I know it's going to be continuous everywhere. In other words, there is a single point that's discontinuous, but we can redefine it. So x equal -2 is a removable discontinuity. So one of the other things you're going to be asked to do is, given a piecewise function, determine the intervals where the function is continuous. And piecewise functions are a little bit different than the ones we just looked at, like polynomials or rationals. However, they have a lot of the same properties. So for a piecewise function, in order to determine continuity, we first need to look at each of the functions within the piecewise. So in this case, if I look at f of x equaling x squared when x is less than 1, x between -1 and 1, and 1 over x when x is greater than or equal to 1. So here my three pieces I'm looking at are x squared, x, and 1 over x. And in general, I want to start there and look at any discontinuities. Okay? So if we look at x squared, this one is a polynomial. We know this is going to be continuous everywhere. Okay. Same thing with x. If we look at that function, again, basically a polynomial function, so continuous everywhere. And then if we look at 1 over x, well, this is a rational function, so we have to take into account the denominator. Here, we can see that x equals 0 is not going to be continuous, so it's continuous except at x equals 0. Okay, so there's the first part. If we look at the actual individual functions and look at our three conditions, it is defined everywhere else, so except at 0. The limits exist everywhere, again except at 0. And the limit equals the function value, again except everywhere except at 0. So there's the first piece. That gives us one discontinuity. The other place we need to look is to make sure the limits exist and equal their function values for the actual piecewise function. And what that means is we need to look at the pieces of the domain and make sure that coming in from the left and coming in from the right, they're going to the same values. So here, if we look at the limit as x goes to -1 from the left, we want to see if it equals the limit as x goes to -1 from the right. Okay? And so here from the left, that would be the less than, we get the limit as x goes to negative 1 of x squared. And from the right, we're looking at this function, so we're looking at the limit as x goes to negative 1 of x. And so here, using our limit properties, we can see this is negative 1 squared, or 1. Here, using our properties, this is negative 1. So these are not equivalent. So this is not continuous at x equals negative 1. So now we've got two values. Okay. We need to do the same thing with our other break. So the limit as x goes to positive 1 from the negative side, and the limit as x goes to positive 1 from the positive side. Okay, so from the negative side, we're back to looking at the x equation. And on the right, we're looking at the 1 over x. Okay, and so here we can see if we put in 1, we'll get a 1. Same thing, limit of 1 over x going to 1 is 1. So this one works. So in this case, we have 2 points of discontinuity. So to find our intervals, we're basically looking at the interval from, so it's continuous on the interval from negative infinity up to negative 1, from negative 1 to 0, from 0 to infinity. Okay, so just not including those 2 points that we found. So one last property that we get from our continuity is this intermediate value theorem. And basically this gives us a way to find values within intervals that are continuous. And the values can be various at this point, but will later lead us to another property that we use later on. So if f is a continuous function on a closed interval a to b, and n is a real number between f of a and f of b, so we're assuming that f of a and f of b are not equal, then there exists a c in the open interval ab such that f of c is equal to n. And so here, if we kind of look at this pictorially, it says if I've got some function that is continuous on some interval a to b, and these values are not the same, so here I have f of a down here, f of b is up there, they're clearly not the same, then there's a point in this interval, it doesn't have to be in the center of the interval, but somewhere in that interval, such that the value here, when I go to look at the y values, here's my f of a, here's my f of b, there's this value c, that's got to fall, n, that's got to fall between them. Okay? And like I said, we'll be able to extend this so we can use nice properties about that value c. Maybe we want the value to be 0, or we want it to be a specific number, but that intermediate value theorem comes in handy. Okay. So let's look at an example of this. Let's say that our f of x is the following function. So x to the 4th plus x minus 3, and let's look on the interval from 1 to 2. Okay. We want to show there's an n in that interval such that, we want to find a c in that interval such that we can find an n that is between the values f of a and f of b. Okay? So here what we would do is we'd start with the open intervals, meaning the open endpoints, the 1 and the 2. And we want to start by making sure that they're not equivalent. Okay? So f of 1, we can see we're going to get a 1 plus 1 minus 3, which looks like a negative 1. And if we look at 2, f of 2 looks like 16 plus 2 minus 3, which looks like a 15. Okay, so those are clearly not equivalent. Okay. So, knowing that these are not the same, then there is a point, which I'm just going to call C, such that the following is true. Okay, and I don't have to write more than that. This follows directly from our intermediate value theorem. Because the endpoints have different values, then within the open interval, there has to be a point in there which its function value is between the function values here. Okay.